Hi, Joyce and Gerardo.
Joyce and Gerardo.
Oh,
Hi,
good
friends.
Hi guys. We started in the back of our spirals and we're doing AP practice. Then we're going to go back to section 2-3, finish him up, go over 2-3 evens, and then go over 2-4. 2-4 is short, he's easy, test is on
Thursday.
Thursday, not Friday. Thursday. Okay, first of all, number 49 and 50, we're talking about continuous functions. Oh, P.S., pause Joyce and Gerardo and do these in the back of your spiral and then come back. Okay, so for definition of continuous, let me do it in black. What are the key components again?
The limit as x approaches a or c from the left, right?
Uh-huh. Has to.
Equal
from the
limit
right.
as x approaches c from the right of f of x.
Has to equal
F of x.
C.
F of c.
And this is the working definition for piecewise. Definitely. So, remember, if we come from the left, we could say less than. If we come from the right, we can say greater than.
Did you calibrate the board?
Yes.
That looks better.
Thanks. So wait, the first part coming from the left, to take a limit, we plug and chug, right? So coming from the left, less than, we're going to choose the first piece, plug and chug, so we're going to set 4 minus negative 1 squared equal to. Because we're plugging in the c, which is, now hold on, why are we dealing with negative 1? Well, hold on, he's a parabola, he's good everywhere. This one's a parabola, he's good everywhere. So if they're both good on their own, what's going to be the only trouble spot? How they come together, whether they do come together, whether they don't. We're trying to make them come together at the same point. And where they come together is at negative 1. So in essence, we're coming towards negative 1 from below, from less than, taking the limit. So plug it in, check. Go towards negative 1 from above, plug it in. So how on earth are we supposed to find A? Solve. And technically you set it equal to f of negative 1. But hold on, isn't f of negative 1 the exact same piece as f greater than negative 1? So plugging in will be the same thing. So then we go ahead and have on that side, let's see, that's 3 plus 1, 4 equals A, right? Bingo. If A was anything other than 4, they would not meet, there would be a break in the graph. So you guys, I'll be quiet because my voice is not strong. Talk me through, how do I do number 50?
Well, the top one is from below, and the bottom one is from above. So you set them equal to each other and plug in 1. And solve for A.
P equals negative 1.
Yeah? Rocking it? So then number 58. I don't want you to tell me the answer, I want you to tell me why. So let's start with Jackie and we'll go around. Jackie, letter A. True or false?
False.
How come?
Because fx equal 1 when x equal 1.
Which means that's false.
Yeah.
Okay, George, letter B.
Oh, the limit exists as you come from the right.
How
Of
come?
0.
How come?
Because the top one, plugging to the top one, right, the limit's 0.
So this one would be 0 positive, and then plug it in, equals 0. Check. Amanda.
No,
That's
true.
Oh, sad day. You're right. So we're done?
Yeah.
That's okay.
Whoa.
Maybe you didn't calibrate it.
I did though.
What?
Wow. Are you touching it somewhere else?
That's my track. No, my tracker wasn't touching it. Okay, why is C false though, Amanda?
Which Amanda?
It's-
Front Amanda.
Oh, me. Why is C true? Because when you're going on the third function, the negative x plus 3, you can plug in 2 from the negative side.
And then we'd end up with
1.
1. Oh, it's not true. True. Amanda Debasarian. D.
Well, when one exists because like the second equation says it exists.
The second one says it exists. Yeah, and what would it be? Oh, careful. Going towards 1, we'd have to come from 1 below.
From the left and from the right.
And then 1 on the right. So then 2, and then 2, right? Okay. And then back to Jackie.
Except hungry.
That's true.
Oh, Sam.
Oh.
Letter E. Why is it true? Because Gerardo's not here.
So everybody did the calculation, right?
Yeah.
It's 2, but at x equals 1 it's 1, so it doesn't matter.
Look at that.
Job, Sam.
Always
Pro
you.
status. So then A is the right answer. Yeah?
Yeah.
We.
So let's go back to notes. I think this is where we ended on Thursday with the difference between removable and non-removable. Oscillating is a non-removable, and jumps, like defined by a piecewise, are removable. Just something to keep in mind. But remember, breaks or not, if the one-sided limits do not meet up, that's non-removable. There's technically like a whole exploration you do, but
We got it. We're chilling.
it was basically, yeah, just talking about piecewises, and I think with what we did at the beginning of class, we're okay. Alright, a few technicalities. This right here. A few technicalities. Just because on the AP they won't require you necessarily to worry about this, but in college math, I don't want you guys to have the idea wrong. I really am not sure I have taught in the past continuous function properly. Because a continuous function is a function continuous everywhere. And then usually that's where I stop. However, that's not the true definition. Everywhere in its domain. Now, why does that make a big difference?
Because everywhere would be different for x squared, because it would be going up, not, wait, no, that would be this range, my bad.
X squared is continuous everywhere, and it's a continuous function. 1 over x is not continuous everywhere, but it is a continuous function. Why?
No breaks, jumps, no limits.
There's no breaks, no jumps, except at x equals 0, which is not in its domain. So that makes a difference, and it just makes it that much more important that we can figure out domains really quickly, which hopefully we can, but I just wanted to make sure that was true. So something even like square root of x, it's not continuous everywhere, but once again, it's a continuous function. Why? Because obviously, look at it, it's only for x greater than or equal to 0, no jumps, no breaks, okay, it's continuous. Just something to keep in mind. On a closed interval, I actually have a typo. There technically is a little add-in to what it means to be continuous. This spacing is bugging me just a little bit. There we go. And all of this kind of just leads up to an example like, and hopefully we know what this is. My question is, where or for what x values is the following function continuous? My question is, where or for what x values is that function continuous? And you can't completely properly answer it unless you use the ideas found up above. Who is it? What is it? What is this?
X or square root of x, no, it's a line.
Not a line.
It's a circle, half a circle.
It's a half circle.
Oh, okay.
The top of a half circle. Half. Now, George, you are looking at it and you are saying square root of a squared, so it has the degree of a line. Which I kind of understand, I would kind of agree. If we were doing like a rational function test thing and we were dividing. But in essence, the graph itself is a half circle with a radius of 9. Because if we were to square the other side, we'd have y squared, x squared, move it over, x squared plus y squared is 81. But my question to you is, Its domain is from -9 to 9, including, but where is it continuous?
From -9 to 9.
True, but why, if we just use the old definition of continuity, why would it not be enough to actually let us state this without this little quick add-on? What could pose us some problems?
F of.
What's the limit as x approaches -9 from the left?
Oh, it doesn't have a left.
Doesn't. How about as x approaches 9 from the right?
It doesn't.
Doesn't. But why am I still able to say this function is continuous on?
Because on the. Is it open or closed?
Closed. So we can state a function is continuous on a closed interval. As long as it's continuous in between, it is. And it's continuous from above the left endpoint and below the right endpoint. Above the left endpoint and below the right endpoint. As long as its function is continuous in between, check. It's continuous as I only come from the right, check, and as I only come from the left, check, then I can go ahead and make this statement. Just something quick so that we can have the technicality down. George.
So, it wouldn't be an open interval because, but isn't it because like you can't come from the right?
The open interval is true as well, but we can go further and say the closed even though we're not able to come from the other sides.
Okay.
Does that make sense?
I'm just wondering why we can do that. It's just because everything else is continuous.
Because there's like a
between-
corollary to continuity and what it means to be continuous on closed that makes it legal.
Okay.
Okay. After that, this one is basically what we just did at the beginning of class. Is it the exact same one?
Yeah.
Sure looks like it. Okay, then we're not going to do that example. Let's keep going. Ah. There we go. IBT. IBT, I'm going to ask you a question a little bit different than I did last year. You don't necessarily have to write them down because you guys should have them memorized anyway. However, some of you never really got them well memorized the first time. We know the idea, so let me get rid of the graphically. And let me instead give you an interesting example. Which is actually in the new Calculus AB book, and I like the idea. We do this with MVT. We even do this with roles, but we don't or haven't done it with IVT because I haven't really had a way. But their new book figured out a way. So let me give you. See if we can interpret the directions and go for it. To figure out, does IVT apply, number one? And then if so, find me C. Just for sake of practice, don't start with finding C. That should be the last thing.
And we're using only IVT, right?
Only IVT. Are we doing t-shirt sales today now? Or is that next week?
Next week.
Do we have a meeting today?
We probably should. But the only thing is we still don't have the final design. We never got it back. So I don't know who has the final design.
Sarah was working on it. I don't know if she got it back. Do you want a group chat and just double check with them? Yeah.
Nikki's not here. I don't think Cameron's either. Actually, that could be a problem.
Your camera's on.
That's what I was thinking maybe we should.
Tomorrow?
Maybe. In the group chat, once you like to have it, were you planning on a meeting today? I think Nikki and Cameron are gone. Do you want to delay till Wednesday or something? See how we just want to do right wrong. This one's better. All right, what are we doing? How are we determining whether IVT applies?
We have to check and see if it's continuous.
Okay, first of all, check and see if it's continuous. And this function, f of x, is continuous for,
X does not equal 1. For all x such that x doesn't equal 1.
yeah. Why is that okay then?
Because that's not within a row.
Right, 5/2 is 2.5, so therefore, since x equals 1 is not within, the interval they've given me is not within a to b, is not a problem. So therefore, f of x is continuous on this interval. Check on 5/2 to 4. Okay, what's something else we have to check to see if IVT applies?
F of
A is within f of A and f of B.
Yeah, we have to see is 6 in between f of, well, I need to find f of, right? Who's f of 5/2 and who's f of 4? What'd you guys find?
35/6 and 20/3, unless I did my math wrong.
Which one was which?
The first one, 5/2 was 35/6. And then 20/3.
20/3? Do you guys agree?
I didn't do it. I'm sorry.
But maybe you got the same ones.
Oh, I'm just like guessing. I didn't do it either.
16, 4, 20, 20/3. Yeah, that's good. And then 5/2 is 25/4.
And 10/4.
Plus 5/2 would be 10, would be 35/4 all over.
2 halves.
Mm-hmm.
And then you flip it, so 2 over.
And the 2 and the 4 cancel, so 1 and 2, and then the 3 doesn't cancel, so then 35/6. I think that's right.
And then
Uh-oh, but what's the problem with that?
it's not with, it's 6 isn't within it, right?
Well, this is less than 6, 5 point something true, and then this would be, greater than 6, yeah?
Oh, it is? Okay, cool.
Because that'd be 6 2/3. So we have 5 and 5/6 and 6 2/3, so therefore does f of c fall between?
Yes.
As or equal to, right? Yeah. F of 5/2 and f of 4. Okay, cool. So now what?
Okay, cool. Then there exists at least one number c such that f of c equals k. Or one number c within a to b.
Okay. Such that f of c, which would be c squared plus c all over c minus 1 if we were to be all specific, equals 6. True?
Yes.
So how do we solve?
Cross 6c minus 6 equals 6.
Right?
And then c squared.
Does that look good? So we factor and we end up with
2 and 3? Negative 2 and positive.
C minus
So negative.
3.
Wait, wouldn't it be plus 6?
Oh, struggle. Yeah, it would be. In which case we could use 2 and 3. And it'd be minus minus, right?
Yeah.
It's the easy stuff. Wait, 2 answers? Okay, fine. That's not necessarily wrong, but
there's, at least one number, so we have to check.
yeah. Are both of them guaranteed?
No.
Which one's not?
2.
2.
Yeah, because 2's not within a to b, so therefore the only guaranteed one would be c equals 3. They both make the same y value, but the only one that fits in the condition or the conclusion of IVT. Anyway, that was an interesting problem. We hadn't gotten to see one of those before because I just hadn't known how to work it before.
That's
There we
pretty
go.
interesting.
Are we good? And with that, we're done. Homework number 5, section 2.3, spirals open. Let's go check our evens. See if you guys had any questions along the odds. Do this. So evens, we had 2, 12, 20, 24. Start with number 2. Basically, everything is good except for the zeros with the denominator, meaning 1 and 3. Why did they say infinite discontinuities, otherwise known as non-removable?
Because it's a jump
Oh, I wrote the wrong.
or it's a
I
break.
did number 3. That's sad.
Sad day. Oh, number 3 was nice. He's continuous everywhere.
Yeah, that's why I liked that one.
Why is it called infinite discontinuities? Remember they had some new terms?
Is it?
Because it's a vertical asymptote, yeah.
No? Oh.
Because they don't factor out, right? So it's not a whole, it's not removable, it's non-removable. And if you plug them in, you get number over 0, infinite. I lost track. What's my next one? I literally just looked at this a second ago.
Number
12, 20. There's number 12. A, yes. F of 1 equals 1. B, yes. Limit as x approaches 1 of f of x is 2. C, uh-oh. No, D, no.
20 is next.
Basically, limit doesn't exist and it's not continuous, or they don't agree. And it's therefore not continuous. Number 20, right?
Mm-hmm.
At x equals 2, removable. How do we fix it? We set f of 2 to equal 1 instead. We just change the piecewise. Not that we're just like allowed to play God with the function, but saying that one quick correction could go ahead and fix it, just like canceling out could fix it. Then number 24. It's not continuous outside of the domain, which is kind of implied. However, other discontinuities are at 1 and 2. That's what it's asking, right?
Yeah.
Then letter B, 1 is non-removable because it's a break. The one-side limits don't agree. X equals 2 is removable because you just have to move the point. Okay, next one.
28.
28. Nice thing is this is being taped, so if for some reason you fell behind, you know what to do. Number 28. This could just be a trick that we saw from last year, and that the limit is 4. And so in order to extend it, that's just saying to make it continuous, you just need to say, hey, the limit is 4, so therefore I just need, at 0, I need it to equal 4, and it'll all match up. It'll fill the hole. That's what's going
Is that
on.
what it was asking?
Yeah, does that make sense? So you're extending the function in order to fill the hole. So you're assigning it piecewise and saying, hey, everywhere but 0, sweet, use your function, but at 0, it's a hole. That's okay. Fill it, make the y value 4, and then you've made it continuous. You've made it continuous. What's the number next one?
42.
42. Yeah, this one okay.
Oh, this one you could really do whatever you want.
Yeah,
so.
you seriously could. You just needed, I think, didn't they tell you what the limits needed to be, the 1 and 2?
Yeah.
Or no?
They said f of negative 2 exists, the limit as x approaches negative 2 from the positive side of fx equals f of negative 2, but the limit as x approaches negative 2 does not exist.
Oh, so yeah, it didn't even assign exactly where it had.
Yes,
It
you
did
can-
assign this one
Yeah.
in the sense of it needed to match up. You just needed it filled on the right and then empty on the left.
Yeah.
And having fun beyond that. All right, anything else? Any more evens?
Can we go back to an odd though?
Yeah. Oh, we still have 48. Hold on. Right? Oh, he's over
Oh,
there.
48.
A equals 3. Okay, go back to an odd. Which one?
31. Oh no, okay, this one makes sense then with your new definition of
Yeah,
continuous.
a continuous function. Because of this domain. It just makes domain that much more important, which domain should be, but there is a discontinuity at x equals 3, but it's in the domain. Outside. X not equal to 3 is the domain, so therefore we can say f is continuous. Good question. Any more odds from anybody else? Going? Sweet. Let's finish off chapter 2. Everything with limits and continuity and IVT, etc., etc. So, boop. Nope, we already did that. There we go. Rates of change, didn't we already do that? Yeah, kinda. Tangents, should kinda know that one too. And sensitivity, ooh, that's new. Pretty much. 2 old, 1 new.
Are you sensitive?
I don't think we specifically, sometimes. I don't think we specifically, graphically, even though you guys should know. I know Gerardo was working on it over the summer. We didn't specifically talk about average rate versus instantaneous rate in terms of lines. We have the secant and we have the tangent, obviously. In section 2.1, we already did average rates. You guys know that's over a time interval from one time to another time. That only gets tricky when they give us rate. You need to find the average. That's an integral formula that we'll get to soon. Otherwise, we're just plugging and chugging into a slope formula f of b minus f of a all over b minus a. Or I should say the position function x of b minus x of a all over b minus a. Instantaneous rate, we know what we're doing with the tangent line. There are going to be plenty of places to cheat with derivatives this section, but
I love cheating.
that's good. But you guys know, especially you guys, know that the AP can definitely give you things in different forms that you need to be able to know as a derivative. Now, we practiced it well last year, and we practiced it a couple times this year. But just remembering, knowing, making sure that we know that all 4 of these things are synonymous. What if they don't tell us slope of a tangent line, but they just say slope of a function at a point? They're referring to a tangent line because it's at one point. Obviously, if they say slope of a tangent line, it is what it is. The instantaneous rate, obviously, that needs to be a derivative unless we already have a rate formula, then we're just plugging in. And then we have number 4, which is the difference quotient, so therefore it's a derivative. Instead of there being an x, there's an a, so therefore it's a particular derivative. However, do you guys remember the other way? This is one way of representing a derivative with a limit, but there is another way at x equals a.
Was it plugged in?
Yeah, with it plugged in. But how is it plugged in? There's another variation. I think we've seen it once or twice this year already. This one has the x plus h, the x, but x is equal to a. What's the other way of writing it? You guys know. I'll start it off. Does that help? There's no h. You need to make it 0 over 0. How would you finish it?
Is it minus f of x plus a over
No.
x minus a?
Because that would be f of a minus f of 2a. That'd be different. Remember when we plug in, it needs to
yeah.
cancel out. So what would that have to be?
A.
Mm-hmm. Right? Because then I plug in f of a minus f of a. What's going to be on the bottom? X minus a. Those are the 2 different variations. Now, of course, they're going to be like, hey, find the slope of the tangent using the definition. If they specifically say use the definition, I want you to use it just because that reminds your brain of what it looks like plugged into the limit form, so that hopefully we'll never miss one of those AP questions. Yeah? But otherwise, if it just says like, hey, find the equation of the tangent line, go ahead and use power rule, whatever, find some derivatives and just make sure that they all match up. Cool. Now, historically, I did find two things kind of fun. Now you have to write these down. They're not going to be on your quiz or test. But I thought these were kind of fun. Your book has tons of different historical things in there. I had a whole class called History of Math back in the day. That was fun. I think I've shown you guys even my book. But for Ma, he had one of the $1 million problems. He scribbled in this margin of a page, the proof of this. There's not enough room in this book to write, and so I'll write it somewhere else. And he never did, and then it took us, he was around 1629, the Millennium Problems, that's 2000. So anyway, it took us a while to figure out how to do it, and I think someone's finally done it. But he was the one that figured out how to use tangents. And the interesting thing is he started using tangents as in tangent lines in order to solve the problem of the cone of greatest volume that can be formed by, hey, wait, a cone of greatest volume, what kind of application problem is that? What was he trying to solve that made him start using tangents? Greatest
Area.
volume? Oh, come on.
The integral, right?
Greatest volume, maximizing volume. What kind of problems were those? Not related rates.
Optimization.
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 He was doing an optimization problem, and that led him into figuring out the method of tangents or using tangents. And specifically having the secant lines getting closer and closer and closer to the tangents by having h approach 0. Anyway, that was interesting. And then, if you ever wondered where normal came from, because normal, that's in the section 2. If it says something about a line normal or a slope normal, what's it talking about?
Parallel? No. Perpendicular.
Perpendicular. And what's the relationship between the slopes of perpendicular objects or lines? Flip it
Flip it
and
negative.
opposite. But why is it called normal? Because they're not weird? No, because it came from Latin. In Latin, the word normalis meant perpendicular, became normal when they were trying to go into English to let everyone else know what was going on. Anyway, I thought that was interesting. Okay, last thing. I'm not talking about tangent lines. Why? Because we know how to make lines, point, slope, form, and then tangents, take the derivative, plug in, unless they tell you to use the definition and then use one of these variations, or use the general one, plug in x is a at the end. But this is new. Sensitivity. It's another application that AP does not test. However, it is another application technically of derivatives. Somewhat has to do with measurement error, which we have done before, without an estimate error, percentage error, propagated error, etc., which is coming. But sensitivity, I just thought was an interesting application. Basically is talking about with a slight change in one variable, how is another affected? They gave examples as far as like rains and crops, in the sense of depending on how much rain has already, and this one makes sense, I think medicine does too, but I think the rain one makes even more sense. Depending on how much rain the crop has already gotten, or how much rain the crop has already gotten affects how much an increase or decrease in that rain affects the crops. In the sense of if the crops haven't gotten any rain and they start having, it doesn't really matter much, it's going to be pretty sensitive in the sense of reacting to how much rain it's gotten. However, if it's gotten a lot of rain, is it really going to make a huge difference if they have a little more or a little less? Probably not. The same idea kind of applies to medicine in the sense of dosages. And in this particular example, we're talking about a medicine that is supposed to lower a patient's temperature. And depending on the dosage, how much is being given to the patient will affect how much a little change, a little additional dosage or a little bit less, which you can't really take away a dosage once you give it to a patient. So basically it's, if you give them a little more, how is it going to affect? And why is that important? Well, you don't want to overdose the poor person, number one. Number two, if you give a certain dosage and it's like, it's not coming down, I need to give a little bit more, you want to be able to get it down to an acceptable range, and you want to figure out exactly how much more you should give. But it does depend on how much has already been given. So there's a little formula in the sense of the sensitivity with the medicine, with the limit as delta D goes to 0, delta D meaning change in dosage. goes to 0. Change in T for the specific one is change in temperature. So the change in delta, I bumped the board. The change in the dosage, a little bit additional, will change the temperature. But how much? And we can say approximately because we can look at this formula, we can kind of move it around. And remember, approximate, we're taking out the actual derivative aspect. We can go ahead and multiply delta D up and say, okay, so approximately change in temperature is the sensitivity times the change in dosage. So specific one, person comes in 102, is given medicine to lower the temperature. As a function of the dosage measured in milligrams, the patient's temperature should be 99 plus 3 over 1 plus D. Find and interpret the sensitivity of the patient's temperature to the medicine dosage when D equals 1 milligram. How do I figure that out? Plug in 1, 2.
So we go from 0 to 1 in,
Whose sensitivity? So if I want to find sensitivity, I'm not using sensitivity, I'm just finding sensitivity. What do I need to do?
find the change in T and the change in D,
Uh-huh,
and then take the limit.
uh-huh. But how do we actually apply that?
So we plug in 102, and then no.
Yeah.
Are we going to cheat and find the derivative, or do you want to do it the limit way?
Let's cheat.
The limit way?
When you first plug in 1, and then you get 99 plus 3 over 2, and then 102 minus, that would be the change in temperature, right?
Between two specific times. But remember, if we're doing as delta D goes to 0, we're not just talking about those 2 times. Because that would be like average. So instead, technically, to find sensitivity with the limit definition way, we'd have to actually find the derivative, which means the limit as, we could do delta D as, there's a few different ways. I'm trying to do it x equals 1. We could do as D approaches 1, of D minus 1, and of T of D minus T of 1. That would work. Using what we saw just a second ago in the sense of like x and a. D is like our x value. So then we could go ahead and get our limit as D approaches 1, D minus 1. And then Amanda, you already plugged in, and you got 3 halves.
Yeah.
Wait,
Plus
99
99,
plus- Yeah,
so-
99 plus 2 halves, so 101
101 and a half. No,
Okay.
Oh,
100
and a half, which would be 203, right?
Yeah.
No, that doesn't work.
No. Math is really hard sometimes.
It'd be 100 and a half, right? Which
Yeah.
would be,
201 over.
there we go.
There we go.
And then we'd have our, well, hold on. There's a 99 that's going in. That's silly. Why are we doing that?
Oh, factor that.
Wouldn't that be easier?
Yeah.
So then our 99s just cancel anyway.
Oh, there we go.
And then we would technically go ahead and, obviously it's 0 over 0, right? That's what we're doing. We'd multiply top and bottom by 1 plus D. So we just have 3 minus 3 halves. You guys see me simplifying my complex fraction, yeah? So we'd have D minus 1,
Shouldn't you have a 1 plus D next to the 3 halves?
3 halves times 1.
Also 3 halves D.
There we go. And then 3 minus 3 halves is just 3 halves again, right? Positive 3 halves. Pull out a positive 3 halves. That'd be a positive, so that'd be 1 minus D, which would be the same thing as pull out a negative D minus 1, right?
So then we got negative 3 halves over 1 plus 3.
There we go. And then go ahead and plug and chug. So we have negative 3 halves over.
2, so 3. Negative 3.
Ah, close.
Negative 6 over 2.
So we'd have negative 3 over 4. Right, because the 2's combined. And that would be our sensitivity. Why is it negative? Why does that make sense?
Because it's less sensitive.
No, not less sensitive.
It's more sensitive to
As the dosage goes up,
sensitivity goes up.
the temperature goes down.
Oh, okay.
So basically for every milligram, that'd be degrees Fahrenheit per milligram. So for every additional milligram, the temperature will go down 3/4. Now homework really isn't bad, guys, like it's mostly tangent lines. I think I have 1 or 2 sensitivity questions, just 'cause I thought it was interesting. But besides that, homework 2-4, have it ready for tomorrow. Joyce and Gerardo. Gerardo, hope you're feeling better. Joyce, I think you're here, so we'll see.
Yeah, so
All right. Bye, guys.